You know about APOD? Great website. apod.nasa.gov. Astronomy picture of the day. This is today's picture. Every day there's something on here. I think you would find it very interesting. There's a lot of stuff. Scroll down to the bottom, and there's an explanation of what you're looking at with links so you can learn more about it. This is a photo from Hubble, I guess. Yes, sir.
Are these photos like actual photos from like the thing that's flying in outer space, or is it like, like a computer simulation?
No, these are actual photos, but they've been, the colorization is false color on these sorts of things, because if you look at this with your naked eye, you can see this object with a telescope, not with your naked eye, and it would just be white. So they use different filters to filter out the different gases. So they use emission spectra, and then they'll use a filter to pick up on certain elements, that emission spectra, and then they'll have a different filter for different elements, and then they'll combine them, and that's why it has all this color to it. If you saw it through a telescope, you wouldn't see this kind of color. So, but it's a combination of several photographs taken with different filters. It's a real photograph. Yesterday's, I sent that to you. Did you see it? Get a chance to look at it? No, not yesterday's.
In the video you showed us, that was a simulation, right?
No. That was all real.
Like software done.
No. That's all real. This is we have a probe orbiting Jupiter, and this is real photographs.
How long did it take to get there?
It took years to get there.
Like
but
10, 30 years?
Probably more like 10. You can shorten the time if you use gravitational assist, so you fly around Venus or fly around Mars, and that speeds it up. So beautiful stuff. And so these are actual photographs. This is not a computer simulation. Pretty cool stuff. Interesting terrain. This is Ganymede, one of the satellites. You can see some of it looks a little stitched together, so that they might have pasted together close-ups or something. I don't know, but these are all real photographs. This is taken last June, so it's orbiting around Jupiter and flying by satellites like that. Close-up pictures, like analysis of the materials on the moon, and then you'll see up here coming up. It's going closer to Jupiter now. We're turning the camera. There's Jupiter. It's coming in close. This last June 8th. So the sun is weird down to the bottom left. What are the splashes? Light. I might turn that. It's pretty music, but it doesn't really change what you're looking at. Yeah, lightning. You can see the flashes are associated when you get into where the sunlight is. You can see the flashes are associated with the cloud structures on Jupiter. Some of the flashes sometimes are meteorites hitting Jupiter. Comet hit, I guess, was Jupiter and Saturn. Well, Hubble was watching it, so it got some really good pictures of that.
And I heard they call it Jupiter like a gas planet or something.
Yeah, it's mostly gas.
So does that mean it doesn't have like a solid core?
It has I think a dense core, but it's not rock.
Oh man, weird. It's not like iron.
Yeah, it has a magnetic field, and so it's the production of Jupiter's magnetic field is different from the Earth's, because the Earth has a rocky core with molten iron center. Jupiter doesn't have iron in the center. So it's interesting, by the way, to try to understand why some of the planets have the composition. Like the rocky planets are the inner planets, and then the outer planets are gaseous planets. So it's just pretty cool. So I highly recommend it. You'll see a lot of interesting stuff there. And then you can go back, you can scroll back to the previous days, and then just some of them are more about science than others. Some of them are, just kind of descriptive things you might see in the sky, this evening. So highly recommend. It's pretty cool. Stop sharing.
potential of the quantum mechanics to figure out what those things like how they tell if it's a gas planet or anything, or
No.
like or substances or
Well, the spectroscopy, right, involves understanding atomic spectroscopy, so you can figure out what if there's an emission or absorption line that you can look at, you can analyze composition. So quantum mechanics in that sense. Okay. With regards to homework, I'm very glad to have you working together, to study together. That's really part of the physics culture, right? To work, do homework together, and ask other students what they think. Teaching each other, you're learning from each other. You learn about who understands what he's doing, who doesn't. There are things that you learn from each other. But when you really need to take the time, though, when you're working out homework, to do it, write it down on your own, because you really learn a lot that way. So, it's okay if you work together at some level, but then when it comes to writing down the solution, do it on your own. Okay, because you really need to do that. You need to, because you learn it better. You do that work yourself. Okay, does that make sense? Yeah. Okay. All right. So I was trying to get a video. I guess we'll talk about Max Born later. All right, so let's recall some things from E&M. So we had a thing called a charge density. In 3 dimensions, if we multiply the charge density by a little volume, and this is going to be the net charge inside of that volume. So this can be a function of location. And so multiplied by a little volume, and that tells you the net charge inside. Remember, in electricity and magnetism, we developed the empiriometric theory. We had 2 types of charge, and we assigned them plus and minus empiriometrically. They're really just 2 different kinds of charge. But it works empiriometrically because they have opposite effect in some way. Like charges repel, unlike charges attract. You can keep track of all that stuff by having a net charge density. So it could be you have a volume that has lots of positive and negative charges together, and that charge would be 0. They're exactly balanced. Okay, and then we had another thing. So this is a volume charge density. We had another thing, which was a current, a volume current density. If all of the charges were of the same kind in this little volume and all moving in the same direction. So suppose your little volume here has a bunch of little positive charges and they're all moving in the same direction. Suppose it's like that. In that simple case, when the volume charge density has the simple relationship to the current density and the velocity. And the relationship between the current volume current density and the current is you take the product with an area, and that gives you the total current flowing through that area. So this is the total charge per unit time flowing through the area, VA. So if you have a wire carrying current distributed over the volume, so you have a current density evenly distributed in the volume, multiplied by this area, and that gives current, which is normally what we speak about, how much current is flowing in the wire, not the current density. When it comes to electrical applications or circuits or things, you talk about total current. You're talking about the material properties, it's the current density that you're interested in. Okay, and finally, there's this relationship in 3 dimensions. The divergence of the current is related to the change in the charge density. So if current is like this situation, if current is flowing outward from a point, for example, from some volume, then so if J is flowing outward like this, which is a diverging current, then you're losing charge here. So it's a conservation of charge. So this is the conservation of charge equation that says that if charge is going to leave some volume, then it has to do so by flow of current through some place to get out. Okay, so this is to remind you, if you had my section, we talked about the divergence in 3 dimensions. In 1 dimension, let's look at how this works in 1 dimension. It's a little bit simpler. In 1 dimension, you have current flowing only in one direction. Then what you have is divergence, is the derivative of the current with respect to x. So how do you have current diverging in 1 dimension? Well, you might have, for example, current that flows outward from some section here, that's flowing outward to the left, outward to the right. So that would represent then current that's flowing, diverging away from this region. So there's a loss of charge at that point. So that one-dimensional version of the charge conservation equation is very similar to something we're going to see right now in quantum. So remember this. And rho current density in this relationship between. So you could say the average speed of the particles carrying charge can be found by dividing the current density by the charge density. That gives you the measure of the speed of these particles. In copper or something like that, they do very fast approaches to the speed of light, very fast. Good fraction speed light. So that's a refresher. I'm trying to help you to remember this because we're going to find something a lot like this from quantum mechanics, where instead of the charge density, we're going to have a probability density. So we're going to have an equation like this, where this is going to be the probability density on the right-hand side. So we're going to have a current density, probability current, not charge anymore. It's the ensemble probability. So the total probability is conserved. That means if the probability is moving out of some region, it has to be by flowing a current, probability current will flow from one region to another. So what we're going to be looking for is a current density, probability current density. We're going to get that for Schroeder. Any questions about the E&M? Just to refresh your memory. So we're going to find an equation like this. Instead of the charge density, we're going to have a probability. So we're looking for the probability current that's associated with that probability density. And then we'll go back and study some of the problems that we looked at before. We have electrons coming into like the delta barrier. Some of them are bouncing off, some of them are going through. We're going to look at that in terms of the probability current. Okay. So that's the motivation for what we're about to do. We want an equation like this, one dimension. So instead of rho, instead of a current density, we're going to have a probability. Instead of a charge density, we're going to have a probability density. So in E&M, charge density has that relationship to the current density. We have the divergence of current in one dimension shows up as a change in the charge density at that point. Now we're going to use the same symbol J for the probability current. We're going to have have the same equation, except we're going to replace the current density with the probability density. Yes, ma'am. I was about to draw a box around it. I decided to write the capital P here instead of the rho. Make it clear. Symbols are similar, but they're different. Yeah.
You're calling it capital D, the lower bar below it. You're calling it capital P or?
Yeah, it's capital P.
And what he's saying, that is the probability density.
Yes, capital P is the probability density. So we have a wave function. Solution of Schrodinger's equation. Let's write that down. Time-dependent Schrodinger equation. We need to use the time-dependent Schrodinger equation because we're talking about probability density that's shifting. So not pure mode. In general, we have something else because pure mode, the probability is stationary. So we have in a more general case here, we're going to use the time-dependent Schrodinger. Okay, so let's suppose we have a solution, for example, of the delta function barrier, scattering off of the barrier. How do we get to the probability density? So in general, the probability density is a function of x and t. Probability it varies in position and can be changing in time. Yes, ma'am.
Are those two p's the same? Is the probability density the same as the charge density?
No. No, it's just analogous. It's an analog. It's an analog. I do this in the wrong place. They're analogous. So we're going to come up with an equation like this, except we're going to replace it with probability density. And so we're going to have, instead of conservation of charge, we're going to have conservation of probability. Which means that if the probability density is shifting in time, there has to be a current associated with that shift. So we're going to take the Schrodinger equation with this definition of P, and we're going to find a J that works with that. So we're going to look for a probability current, not a charge current, but a probability current. So it's analogous to what we did in E&M last semester. Okay, so we have this thing on the right-hand side. We want to take the time derivative of P. P is psi star psi. So the time derivative of P, the current of the probability density, has two terms in it. Okay, it's now you start to see how we can make this start to work. What's the next step? Put that term right there. Where do we get the time derivative of the wave function? Each Schrodinger equation. The Schrodinger equation tells you how the wave function is changing in time. So we're just going to substitute this. We're going to take the 1 over IH bar, put it over on the right-hand side. So we're going to substitute the Schrodinger equation right there. So we have d psi. I need to move this over here. So it's minus I over h bar times this. Yeah. Okay. That's going to go here. sense? Follow me so far? All right, now we have this other term. So that's this one. That takes care of this. We're going to multiply this by psi star. All of this by psi star. I'm going to substitute this into here and then multiply by psi star. Now we have this term. We multiply by psi and add those two together. Where do we get that one from? It's the time derivative of psi star. Yeah.
So you can just take the complex conjugate of.
Take the complex conjugate of the Schrodinger. Okay, what's the complex conjugate of the left-hand side? Right. And then we have here, well, there's no I left here. This is real. This is real. So it's just psi star. So this is the same equation, just written for a complex conjugate. So if this is the equation for the wave function psi, this is the equation for its complex conjugate. You only need one usually. As you find psi of x, then you multiply it by its complex conjugate on probability. Okay. But it's really the same equation. The only thing is that it has a negative sign here. So it's not an entirely different equation, it's just got a different sign in the front there. Okay, so we're going to substitute that. We're going to find d psi star. Like that. And we're going to substitute that here. Okay, so this has two terms in it. This has two terms in it, so we're going to end up with 4 terms. But 2 of them are going to cancel each other out. So let's write it all out. So d psi star, so we have I over h bar. We have minus h bar squared over 2m. Psi star x squared and multiplied by psi. Then we have another term which is h bar psi d psi star. That's this first term here. Substituted in Schrodinger equation for psi star. Conjugate. Now we multiply psi star by this, so we get 4 terms again. And we got 2 negative signs here, so we get I over h bar squared over 2m. I star d2 psi x squared. Then we get minus I over h bar psi d psi star. You're going to have an opportunity to go through this again for your homework. It's detailed out in the book. Doing the steps where you're previewing it, so you'll see it again. Be familiar. Do this in the book. You're going to do all these steps by yourself. He's giving you pretty much everything you need, but you're going to do all the steps yourself to confirm. Yeah.
When you add that, besides making it equal.
Say again?
Are you not adding that?
Yes. Oh, I said equals. Thank you. Didn't mean equal. We're adding 4 terms. 2 of them cancel. Terms associated with the potential cancel out. So the potential is dropped out. That's interesting. It makes it actually a little simpler. Okay, and this is supposed to be equal to these remaining 2 terms. be equal to the derivative of j. Yes, sir.
Is there any significance to the psi star psi in the second or fourth term? Like, is there any significance to that basic probability too? Or is it?
I should have put here psi star and psi star. It doesn't matter. The order doesn't matter. They're just numbers. I'm sorry. Say your question again, please.
Like, is there any significance to the fact that that is the probability equation, or is that kind of just a coincidence?
That psi, why is psi star psi a probability?
No, it's just like, is there any significance to the fact that that's in the equation for the probability?
You mean the time derivative of the probability?
Yes.
No, it comes directly from the fact that the probability density is psi star psi. Right?
Oh, yeah.
So you're always going to have, every term is going to have a combination of psi star psi.
Yeah.
Right? This one happens to have exactly the same combination. This one has the second derivative of psi star, and this one has the second derivative of psi. But there's always a psi star psi combination in every term.
That makes sense. Thank you.
Okay, so the answer is then J. Oh, yeah, keep part. I want to make sure I don't get the sign wrong. That's the answer. So if I take the derivative of this, let's check this. I'm going to take the derivative of this with respect to x. I get the derivative of psi star with respect to x times the derivative of psi with respect to x. And then I get another term which is psi star times the derivative, second derivative of psi. The second derivative of psi with respect to x. That's the derivative of this term. And then I take the derivative of this term. And again, two terms cancel. This one with this one. And we get what I wrote down there. Except I wrote a minus I, and over here I put the minus I down. So this is the current density, probability current density. Notice that we derived it by using the Schrodinger equation. So what it says is that the Schrodinger equation conserves probability. That's a good thing. If it's going to describe an ensemble, you don't want ensemble going away or gaining members of the ensemble. And this is the relationship between that current density and the probability. I can take time to do all these steps again yourself, following the book. Recording, making recording of the class. Go back to this again. So can I erase this? I'm going to keep this, but I'm going to erase this. So let's sketch that again, how we did it. We're looking for an equation of this form. Probability current, the probability density is psi star psi. So we take the derivative of psi star psi with respect to time. And you notice that there's the Schrodinger equation has the first derivative of the wave function. And then we find a j that will match that on the left hand side. We take the derivative of j, the divergence of j in general. Then we'll get the left and right hand side degree. Any questions? Okay, so let's try a wave function. What is this? Had a particular name? Say again? Yeah, it had not just free particle. It's not just free particle. Not just particle in a box. In fact, it isn't a particle in the box. Yes, sir.
Is it a plane wave?
It's a plane wave. And the plane wave is a pure mode solution to the free particle. A pure mode solution, in fact, it is the pure mode solution for the free particle. Okay, so it is a free particle, but it's not the only free particle wave function. It's a specific free particle wave function called the plane wave. What's the probability? Okay, first, what does it correspond to in terms of the particle involved?
Like what type of particles?
Call it an electron, I suppose, or any particle, a quantum particle, a massive particle. It describes an ensemble of particles moving to the right traveling, and they all have the same energy, right? So the energy, this frequency is h bar k squared over 2. That's because it's a free particle. And it also was right traveling. Corresponds to a momentum of h bar k and a velocity of h bar k over m. Do that? Yes. Why is it traveling to the, it's traveling, I should say it's traveling to the right if k is greater than 0. If k is negative, then it would be traveling to the left. And that sign, that keeps up here too. If k is positive, the velocity is to the right. If k is negative, the velocity is to the left. Okay, you remember that? The very first wave function we saw. Back at, right at the beginning of chapter. All right, so what's the probability density? Psi star psi. A is complex. In general, A is complex. The coefficient out front can be complex, and it's important that it's not a real number. As you saw when we did the delta barrier, the transmission coefficient had a, or was the reflection coefficient had an I. So A can be complex in general. So we have e to the I kx minus omega t, e to the minus I kx minus omega t. What does that give? No. Yeah, they cancel out. E to the I theta, e to the minus I theta just gives 1. So the probability density is uniform and independent of time. Kind of strange. Right? This thing is traveling to the right, per se. The probability is uniform and isn't changing. So there's this constant probability. It corresponds to d squared. But we're saying there's a particle traveling to the right. Let's look at the current density, probability current density, and evaluate this using that plane wave. Put it right here.
Should it not be 0?
What's 0?
The current density?
No, it's not going to be 0.
Is it ever going to be 0?
Yes. Sometimes it will be 0. So if dp dt is 0, the divergence of j, or in other words, the derivative of j, is 0. What does that say about j? J is a constant. Same everywhere. But let's see what j is. And substitute that plane wave into here. So right here we need psi star. Well, we got psi star with a star. We have h bar 2mi. Now this is for the plane wave, right? Just the specific case of the plane wave. So here's this a star e to the minus I kx minus omega t. We want the derivative of this with respect to x. What do we get? Now, take the derivative of an exponential e to the ikx with respect to x. Ik times e to the ikx. And we also have an a. Put in here. Okay, so that's the first term. And then the next term turns out to be the complex conjugate. It turns out to be CC means complex conjugate. Complex conjugate of the previous term. Right? This and this are complex conjugates of each other. If I take the complex conjugate of this, I get this. Okay, so what is this term?
The AA star IK.
So we get a times a star, which is absolute magnitude squared of a. We get ik. And the exponentials cancel out, get 1. And then we get a term which is a complex conjugate. So minus right, this is real. This is the only thing that has any imaginary part to it. So we subtract it, flip the sign, take the complex conjugate. Okay, so these signs cancel each other, so it's the same term, just 2, factor 2. So we get h bar, and we have an I in the numerator and the denominator, so those cancel. We have a factor 2. So let's look at that current. It's telling us that there's a current associated with the particles, the ensemble. Here's a current. But the current is uniform, it's the same everywhere. So the derivative of this with respect to t, with respect to x, is 0. Because it's the same everywhere. So the probability is not changing time, and the current density is uniform. So they match the conservation equation for this. Happens in this case, both derivatives are 0. 0 is equal to 0. So in other words, we have current flowing this way. And what comes in the left goes out the right. If I have a section here, I get just as much coming in the left as is going out the right. So the probability inside that interval is not going to change. See how it works? Just flowing. It's like having 3 inches of water on the floor. The water is flowing this way. The height of the water is not changing. That means that the current has to be uniform. Same everywhere. It's a pretty simple case. Not always going to be this simple. Okay, but notice also we said that we get like a velocity. For E and M, we took the current density, charge current density, divided by the charge density. We got a velocity for the particles. Let's divide the current plane wave by the probability. That's h bar k over m. P over m. So that says that the ensemble is represented by a uniform flow. Particles, the members of the ensemble are flowing this way. There's an equal distribution of them around. Yes, ma'am.
I'm having a brain fart. Remind me what little p is, density?
No, little p is momentum.
Momentum, thank you.
Right here. Related to the wave number by Planck's. This is a de Broglie relation. The wave, this is another way of writing this. Remember that k is 2 pi over lambda. So this relates to the de Broglie wavelength with momentum. So this is de Broglie's relation, but written in terms of wave
wave number rather than wavelength.
Okay. So that's pretty simple, a little too simple, maybe. Let's try something else. Can I erase this? No. No. Okay. All right, so this, you remember we had, when we had the delta barrier, we had plane wave coming in and bouncing off. So we had a reflected part and then we had a transmitted part. And the transmitted part was like this, except we had a C here. And so the probability goes like C squared, and the current goes like H bar K over M times C squared. And so there was a velocity. So this describes what was happening on the transmitted part. But in the on the reflected part, we had two waves. We had a right going wave and a left traveling wave. So let's try that. Let's try. And put in two pieces here. This is like what happened to the left of the barrier. When we had a plane wave coming in from the left, it hits a barrier. Some of it gets reflected. Okay, still, it's not a single plane wave, it's two plane waves. It's a superposition of a right and a left traveling waves. So it's two plane waves, right and left traveling. They both have the ensemble still has the same energy. So we have K to the right and K to the left. This is the left traveling, this is the right traveling. It's still a pure mode solution to the free particle. In fact, now this is a general pure mode solution to the free particle. Two waves going together. Okay, so now you're going to do this for homework. Substitute this into here. Just got to keep track of your widths, do all the complex conjugates correctly. All the I's have to be in the right side. Mess up, we get the wrong answer. I'll tell you what the answer should be. Yeah. Substitute it into here. Do all the right steps. See, it corresponds to what we did before. If B is 0, we get what we got before. So now we have minus B squared. What does that correspond to? That's the current coming back. It's the left traveling wave. Has current in the opposite direction. So this is the right traveling. This is left traveling, so they have opposite current. Okay, so now you're starting to understand why we were focusing on A squared and B squared when we were calculating the probability of transmission. We didn't look just at A and B. We looked at A squared and B squared and C squared. Okay, so we had to, this is in region 1 for the delta barrier, X was less than 0. And in region 2, we had C to the E to the I kx minus omega t. And the current in region 2, current density is H bar K over M squared. Okay. And in fact, we find, remember, by the conservation of probability, A squared was equal to B squared plus C squared. Or A squared minus B squared equals C squared. So in other words, the current coming into the delta barrier, so this is J1 on this side, and J2 on this side, the total current is the same. Because you can't, otherwise you'd be storing up ensemble members right here. Have more coming in than coming out. They have to be storing up here in the delta barrier. There's no place for them to stay. These two equal each other.
C is a right track.
Yeah, that's right. This is a right traveling. So this was a sum of two right and left traveling. So the net current coming in, the same as the current going out. So that's the statement of probability that we wrote down. Like this is just rewriting J1 is equal to J2. So write it like this: A squared minus B squared plus C squared multiplied by H bar K over M. We get J1 is equal to J2. Yes.
Will there ever be a case where you make use of the D term?
Yes, that's coming. We did the delta barrier because it's simple. There are only two unknowns. We're about to do one that has four unknowns. So that's why the delta barrier, even though it's a little strange physically to have an infinite potential over an infinitesimal distance, it's kind of strange physically. It's hard to figure out how you do that. But it's easier mathematically. Only got two equations with two unknowns. So this, we're going to, the next one is coming. Yes.
The four unknowns that you're talking about, is that going to be more of a realistic situation?
Yeah, it'll be more realistic. I'll tell you what it is here. As soon as everybody has written down what they want to write. Okay, so remember the upshot was the Schrodinger equation conserves probability. We don't have members of the ensemble leaving the scene or coming in from somewhere. But if the probability is leaving some area, it's got to flow somewhere else. And so that flow is given by this. And again, we get it from the wave function. We're going to start extracting a lot of information from the wave function. So we have this velocity. What is that velocity? It's going to correspond to a measure of a velocity. So we're going to not just measure position now, we're going to start measuring speeds, velocities, and we're going to see how to extract that directly from the wave function. How to get the velocity. Particles in the ensemble. Yeah.
Would you say since that'll be like the average, like so the average speed of the ensemble,
Yeah.
right? Would you also say E would be the average momentum
Yes.
of the ensemble as well?
Right.
What about the M then?
That's the mass.
What about pick up?
They're all the same, right? The ensemble is a copy. Million copy is exactly the same system. Every system has a particle with the same mass. Right. Okay, so so far. But don't mess up your homework. All right. Okay, so here's a problem we will do next. More realistic than the delta barrier. We're going to have a step up and then a step down. So it has a finite width, unlike the delta barrier, which was infinite height, infinitesimal width. Now we're going to have a barrier width and a potential energy height. And we're going to attack it the same way. How many regions will we have now? 3. Region 1, region 2, region 3. So we'll have an incoming wave, amplitude A, and of course we'll have a reflecting piece. We'll have 2 solutions in this region. So there's going to be, could be corresponding to left and right traveling. It kind of depends here. There's a subtlety we're going to look at here. But there's going to be 2 pieces, 2 wave functions that correspond to something like left and right. And how many are we going to have over here? Just 1 transmitted piece Unfortunately, I'm gonna call it E. If you make it script E or something about the energy, it's the fifth coefficient. Skip the F if you like. That doesn't mess you up.
Oh, shoot.
We need more letters.
Need more letters. Yeah, that's why I like bad Greek letters.
Is H safe?
Okay, well, H is not safe now.
It's like
G is better.
G?
Okay, now we have two different interfaces. Remember, the delta variable, we match the wave function and the slope of the wave function, but actually the slope of the wave function wasn't continuous because it had the infinite potential. But now we're going to have the potential is finite. So psi and psi prime are both continuous. So we're going to match psi 1 to psi 2 at this point, and psi 1 prime to psi 2 prime at this point. Now also we have psi and psi prime is continuous here as well. So we're going to have psi 2 is equal to psi 3, psi 2 prime is equal to psi 3 prime. 4 equations. How many unknowns? A is given. We need to find B, C, D, F, G, H, not tell me H.
I think that's a letter. I don't think I think it's O, so that's gonna be a zero.
Oh, okay.
Q.
4 unknowns, 4 equations, 4 unknowns. So it's mathematically a little bit harder, although and it's a little bit simpler because psi prime is continuous here. Before psi prime had to be discontinuous because potential energy. So that makes it actually a trade-off. Got 2 more unknowns, but the equations are a little bit simpler. So there are 4 of them. And the key here is to find the transmission probability and the reflection probability. And we're going to find exactly the same thing. That the transmission probability and the reflection probability add up to the incoming probability. So this is Schrodinger equation. Doesn't matter what V of X is. Remember that term dropped out. So it doesn't matter that I've got a different V. Okay. Question? Yeah. I told you it's just a little bit late, so maybe I'll wait. This is all done in the book. You'll be doing it yourself, right? Come back and watch the video again. Got a screen.
So for a pure mode.
Right. Divergence. Okay. So his question was the pure mode. Remember the statement that we made that a pure mode is also called a stationary mode. This is 0. Pure mode, also known as stationary. We had a pure mode in the box. Pick one mode. Probability wasn't changing in time. So the current density should be, the derivative of the current density will be 0. It might be in that case that even the current density is 0. But it's at least uniform.